And our next speaker is Alan Wen. Alan is a PhD student at Rochester Institute of Technology, and he will talk about simulations of spinning by neutron star mergers with second moment neutrino transport. Alan, you can continue from.
All right, thanks, Behan. As he said, I'll talk a bit about our simulations of neutron star mergers that we're doing here at RIT. So, as you guys may have been hearing about all week, neutron star mergers are very interesting events that give us a lot of data and a lot of physics. For example, looking at GW 170817, our token multi-messenger event, we can infer from gravitational waves that the mass of the system is consistent with a binary neutron star. And gamma ray, X-ray, and radio observations told us that there's a relativistic jet that was launched. And we see quasi-thermal emission in infrared and optical bands that we associate with the radioactive decay of heavy elements that we call kilonova. So combined with these observations, years of simulations have led us to converge on a general picture of what's going on after these mergers. Um, there's a central remnant. There might be a jet that's launched in polar regions, and we have several components of radioactive material ejected in all directions. So to study these systems, we use a set of codes to run simulations. We use Z4C to evolve our spacetime. We use Illinois GRMHD to evolve our fluid and our magnetic fields. And we've coupled that to David Radicche's THCM1 code to handle the neutrino radiation. So we wanted to test how introducing spinning components into our BNS system changes that general picture that I shared on the previous slide. So we wanted an extreme case that we derived from the observations of the fastest observed millisecond pulsar, and we'll simulate three cases, one without spins, one with the spins aligned with the orbital angular momentum that I'll refer to as the plus plus case, and one with spins anti-aligned that I'll refer to as the minus minus case. We'll use the APR-LDP tabulated equation of state, since we know this results in a long-lived remnant, and that's the case we want to simulate. Setting the equation of state and the spin period gives us a dimensionless spin of plus or minus 0.43 about. And we extend the EOS table to lower densities using the Tim's equation of state that remains valid to these values. Since in Jake Halanani's recent paper, he demonstrated that a low atmosphere floor is required to accurately capture the high velocity shock front of the dynamical ejecta without resetting it to atmosphere. We also use a resolution of 177 meters to resolve the magnetorotational instability in the inner accretion disk, which we kind of enforce to be there by setting high initial values of the magnetic field, as is customary. So the most immediate effect of introducing spins in your binary system is it changes how the binary loses angular momentum during the in-spiral. The minus minus case loses angular momentum faster, which leads to a more violent collision, whereas the plus plus case loses angular momentum slower. There's a less violent collision, but the stars bulge outward and spend more time tidally interacting, which leads to these very massive tidal tails of ejecta launched prior to merger. And we can quantify the effect of the tidal tails in the plus plus case by looking at the mass ejection rate. We see that the tidal tails are slower than the dynamical ejecta in the 0, 0 case. There's a delay in when we detect this outward mass flux. And we also see a jump in unbound material flagged by the geodesic and the Bernoulli criteria, which indicate a transfer of energy from kinetic to thermal that we associate with the tidal ejecta being shocked by the dynamical ejecta actually launched at merger. We then see steady mass ejection in both cases driven by neutrino pressure, and an increase at later time driven by magnetic fields, which I will talk about later. Unfortunately, this is the last snapshot I have of the minus case, so going forward, I'll mostly be talking about the 0, and the plus cases. We can see the effects of the tidal tails in the plus case in greater detail if we look at these mass histograms. In the plus histograms, you see a very obvious component that has that's very neutron rich, that's ejected in the equatorial plane and is very cold. And that's the dominant ejecta component in the plus case. Whereas the 0 case, the ejecta is in general hotter, faster, and more isotropic. And I'll note that ejecta with proton or electron fraction less than about 0.25 has been demonstrated to be critical for your R process nucleosynthesis yields, and there sure is a lot of that in the plus case. If we look at our two-dimensional histograms, we start to see evidence of a two-component kilonova that was associated with GW 170817, namely one component that is very neutron-rich, slow, and ejected in the equatorial plane, and a separate component that is more proton-rich, it's faster, and preferentially ejected in polar regions that we associate with the blue kilonova. This segregation is more obvious in the plus case, but you can start to see it in the non-spinning case as well. Let's move on and talk about jet launching. So we observe similar phenomenology as they derived in Carlo Mussolino's paper, where there's two distinct transition points in the evolution of the Poynting flux luminosity. One they call breakout, when the magnetic fields initially confined within the remnant escape the remnant and are detected at larger radii, followed by a sharp increase of several orders of magnitude that they associate with the Parker instability, where the magnetic fields are finally strong enough to overcome the fluid pressure, and then buoyancy then allows magnetic fields to rapidly lift out of the remnant. This is regulated by this P criterion, which describes the relationship between your fluid and your magnetic field, and your plasma is unstable when P is negative. We'll note that the non-spinning case has a lower post-eruption steady state, and as I'll show in the next slide, the Parker instability tends to periodically shut off. We're not entirely sure why this happens yet, but we think it's due to the fact that the polar regions are much less dense in the plus case at the time of eruption, and that the increased baryon pollution in the non-spinning case might be suppressing any type of outflow. So here I've plotted that Parker instability criterion in the XZ plane. Green is negative, which means your magnetic buoyancy is unstable. And if you remember the luminosity plot from the last slide, you start to see the breakout at around 10 milliseconds post-merger in the plus case, followed by an eruption where the polar regions become steadily unstable, and then followed by the eruption in the 0 case that happens a little bit later, and it seems to periodically turn on and off. And in the last snapshot I have of these simulations, you can see that at larger distances, the plus case, the magnetic fields remain collimated to very large distances along the polar axis. And you see a very organized accretion disk that's stratified in your electron fraction. So you do see much neater collimation in the plus case. However, despite this collimation, is this consistent with a gamma ray burst? And an important quantity to look at is the magnetization, or the ratio between your magnetic energy density and your rest mass density. It's then related to your terminal Lorentz factor. It essentially describes how much magnetic energy is left in a fluid element once it escapes the photosphere, and whether the remaining magnetic fields are strong enough to accelerate this fluid to generate non-thermal emission. And if I play this video, you see even in the ideal plus plus case where the polar regions are quite clean, your maximum magnetization is about 0.1, which is still inconsistent with a gamma ray burst, where you see terminal Lorentz factors of the order of tens or hundreds. So if this simulation is inconsistent with gamma ray bursts, then we have to consider the possibility of magnetar remnants launching gamma ray bursts at all.
Alan, you have 2
And
minutes. Yeah.
all right, awesome. So for future work, we want to continue these 3 spinning runs up to about 80 milliseconds post-merger to see what the late time evolution looks like. But to directly compare to a case that is consistent with a gamma ray burst, we want to do something similar as was done in Jay Kalanani's latest paper, where you trigger the collapse of the remnant by changing the pressure support at the core to get a direct comparison. And at the same time, all hope is not lost for long-lived remnants generating gamma ray bursts. We know that it has been demonstrated in simulations or theorized that there's small-scale turbulent processes that can amplify the magnetic fields within the long-lived remnant that can boost your magnetic fields and potentially launch non-thermal emission. And we want to increase the resolution of these simulations using GPU accelerated codes that we're developing for the next generation of the Einstein Toolkit that you may have heard about earlier. And finally, to conclude, magnetic fields, neutrinos, and spins lead to unique physics in neutron-star mergers that leave imprints on electromagnetic observables. And however, it's unlikely that these simulations can recreate short gamma ray bursts without new or under-resolved physics. And with that, I'd be happy to take any questions.
Thank you very much, Alan, for a very nice talk. Now let's have a question